Hey everybody, this is Blake. Sorry I couldn't be here today. I'm actually TAing right now up in 367. So if you need me or have any questions, I'll be up there. Thank you, Dr. Bongard, for letting me do this voiceover. So by now, we're all familiar with the concept of mutating synaptic weights in order to achieve a more fit population. But I was curious to see what would happen if we took the actual joint values and modified the restriction of movement on those values. So I wrote a method that on each generation would replace either a high or low joint limit with one inside the original bounds of either plus or minus pi/2. I also had a problem where my robot kept rolling over, so I modified our original quadruped to allow it to push its arms up over its head and right itself if it flipped upside down. And because I'm a glutton for punishment, I also wanted a quick way to visually confirm whether or not this joint evolution actually had any improvement over the initial robot, so I taught it how to climb stairs. I was hoping I could prove that this joint evolution evolved either a faster or a more effective population of robots. It took some doing, because in my experience, Pyrosim rarely does what you want it to. Our only solution to stop explosion was to limit joint movement, which is difficult when that's the whole point of your project. Once I had the simulator working as I wanted, however, I found a few things. First, the non-joint evolved robots are far more active in their early iterations than the joint evolved robots. It wasn't too long, though, before both the normal robots as well as the joint evolved robots started to show me that they were learning how to climb the stairs. My fitness function was a weighted combination of the robot's distance from the origin and also the amount of light picked up by a light sensor. Because of the height of the blocks, the light sensor is actually blocked from the robot until it's able to climb the stairs. I weighted the light sensor more heavily, and because of this, as soon as Darwinism gave me a nice mistake of nature, I was able to evolve my robots very quickly to actually make it up the stairs themselves. The robots also evolved some behavior I didn't quite expect. Because I boxed them in a square, their position sensors returned a higher value whenever they went for the diagonals. This also helped them gain purchase on the flat surfaces. Going in at an angle allowed them to use more than one limb at the same time to pull themselves up. All of my evolutions were done in population sizes of 15 over 200 generations with an evaluation time of 2000. Anything more than that slowed my computer to the point of unusability. This is all well and good, but how did it actually turn out? The joint evolution robots consistently started with a lower fitness level than their counterparts did. However, over the course of the 200 generations, they usually ended up on top. Additionally, the maximum fitness varied greatly according to the path that the robots took, which was an oversight on my part. Although the paths and subsequent fitness levels of the different populations varied wildly, the results were more or less the same. Robots who evolved their joints gained fitness at a faster level than their counterparts, although this tended to taper off around generation 170. These increases were less severe than I expected, generally between 5 and 10%. Moving forward, I'd like to perform this same experiment on a more powerful computer with larger populations in order to see if there are more drastic differences. Thanks for your time, everybody.